Hello, my name is Yahavi Airan, and today I will be presenting on my project of exploring the journey of sound near a black hole. A little bit more about me. I'm currently a sophomore in high school, and I will be graduating in 2028. So why am I doing this project? Well, imagine that you were falling into a black hole. Now, if you were crying for help, how long would it take for your cries of help to reach an outside observer? That is what I'm trying to model here in my project. Now, before I begin to explain my project, there's a few essential things that you need to know. Black holes. Black holes are an extremely dense object in space where nothing, not even light, can escape due to its immense gravitational pull. Black holes have many different parts, but the three main things that you need to know are its accretion disk, the event horizon, and the singularity. The accretion disk is the hot swirling mass of matter that moves around a black hole, rotating. It is made up of different gases and different parts of stars that the black hole sucks in. All this matter is moved towards the event horizon. The event horizon is a hard boundary that when you go past it, there's no coming back because the velocity needed to escape the event horizon must be greater than the speed of light. And there's nothing greater than the speed of light. The singularity, we believe, lies beyond the event horizon. It is an extremely complicated place and it defies all laws of physics because it is believed to be the center of the black hole and it has infinite density. Now, because this project involves sound, we will need to know the properties of the medium in which sound travels. There's two main things, rigidity and density. If the rigidity of the medium is high, meaning that the particles are more interconnected, the speed of sound will be faster. However, if the density of the medium is high, meaning that there's more molecular mass per volume, the speed of sound will be lower as the object has more inertia. Special relativity says that time is slower in objects traveling extremely fast relative to objects that are stationary. This can be modeled by a simple photon. A stationary observer and a spaceship both have a photon clock, which are synced. For the stationary observer, the photon moves down and then up 2 ticks per second. However, in the spaceship, the photon goes down, and then it will have to travel a longer distance as the position of the spaceship changes in time. So the path of the photon is diagonal, going down and up, taking a longer time. Due to this, the stationary observer will see that the clock is moving slower for the moving observer. General relativity. General relativity is the curvature of space-time. This is because time is the fourth dimension. When objects with a high mass are placed in space, they also bend time. This means that it will take longer to travel a given distance as it is curved. The greater the mass, the more space-time is curved. Gravitational time dilation happens due to general relativity. It is when time passes slower near objects with higher masses compared to time passing near objects with smaller masses. This can be shown in a simple experiment. Person A is standing near a black hole and is emitting a wave with high frequency green light, which moves towards person B. While the wave traveled towards person B, the wave will lose energy when it is moving out of the black hole's gravitational pull. So person A will receive So person B will receive a low frequency red wave. This means that person A is producing more energy in 1 second than person B. In real life, this would mean that person B sees that person A is moving slower, as person B is just losing low level energy. Now that you know the different parts about the background, here are the equations that I used. The first one over here is the frequency equation, which models how much frequency is lost in the accretion disk of the black hole. The special relativistic time dilation equation models how much more frequency is lost due to special relativity in the accretion disk. The last equation right here models how general relativity impacts the time taken for the frequency to travel in the accretion disk. I used Python to model all my calculations and simulations and the graphs. So here's a sample of one of the calculations for the general relativistic time dilation equation. And I use different Python libraries like matplotlib, numpy, and scipy. Here is a picture of what the vision is supposed to be. Over here is the black hole, and the white line over here is the event horizon. The purple dot over here is the emitter, and these are the sound waves. The emitter is the person crying for help. The sound waves travel to the observer, which is the probe or the spaceship, who can potentially save the emitter, and the observer receives the signals. So the red, orange, and yellow part of this picture are the accretion disk. That's the accretion disk. And it's different colors because it models different temperatures, as seen right here. These are the different graphs that I got from plugging in different values for the different variables. So as you can see over here, as mass increases of the black hole, the frequency observed decreases. So the initial frequency was 10,000, but as you can see, as the mass keeps increasing for the black hole, the frequency observed is decreased. Over here, there's two different frequencies, but the calculation is the same. The emitted radius of the accretion disk impacts the frequency observed. So what is the emitted radius of the accretion disk? Well, that's the distance from the event horizon to the edge of the emitter right here. So when that distance increases, you can see that the frequency observed has less change compared to the initial frequency. Over here are the time graphs. As you can see, as temperature increases, time decreases. So if there's greater temperature, then the time traveling, the time taken to travel for the frequency will be lower. Over here, as the mass of the black hole increases, you can see that the time increases a lot. So if the mass of the black hole is a lot, then it will take longer for the observer to get the cries of help from the emitter. As you can see right here, the emitted radius of the disk, accretion disk, as it increases, the time taken decreases as there's less gravitational pull that can affect the emitter. Now, in conclusion, if we emit a sound signal, technically speaking, the probe on the outer edge will be able to hear it. However, realistically speaking, the probe will not be there for approximately 350 years. And 350 years because the time taken for the sound to travel is approximately 350 years. Now, even if the probe attempts to save the person, it will be unable to do so, as it will take an even longer time for the probe to travel to the person, and by that time, the person will probably already be beyond the event horizon and cannot be saved. I really hope that you enjoyed this presentation. Thank you so much.